David contributed to deep learning projects and technologies in several industry domains. He's right now working for Continental, the Deep Learning Competence Center of Continental in Budapest, Hungary. He's leading teams of machine learning engineers who are developing perception systems for cars, and they have a very important mission: saving lives on the roads. So David, over to you.
Thank you very much, and hello and welcome everyone. Thank you for joining my talk today. So what I will be talking with you about in the next few minutes, it will be AI and road safety, basically. So let's get to it. And let me start with these drawings. So this is how kids envisioned the future of cars, actually, 10 years ago, more than 10 years ago in 2010. And this is how they looked at the future of cars. What we can see is that they are very futuristic still. They have wings, but also you can see that they work without drivers, right? So there is some sort of autonomy. The other one has arms. That's another type of autonomy. So at least what we suggested to our kids back then was something that cars are going to be autonomous and self-driving. Now, this is also something how grown-ups have thought about the future of cars. And they are not as much in the past. So they are about 5-6 years ago. They have predicted that by 2020, the roads will be full with self-driving cars, 10 million self-driving cars, and basically human drivers will be permanently on the back seat. And of course, we know that manufacturing companies and tech companies joined in this very optimistic view of the future a few years ago on self-driving. Now, if we do ask today, similar companies and also the most prominent experts of the field of fully autonomous driving, they would say that it is eventually still an active area of research. So we don't really have millions of cars, not even a single one in series production with the full level of autonomy that is meant as autonomous driving. So this has to make us think, of course, it's a very hard problem. So we have good reasons why the world is not yet there. So us, AI experts, practitioners, engineers, researchers, we have still a long road ahead of us to reach fully autonomous driving at mass production scale in the world. Yet, there are some other aspects of motivation that we must think of. So if you look at these statistics from the World Health Organization, there are more than 1 million roads accidents that result in fatalities in the world every year. And eventually over 90% of them affect low to middle income countries. So if we think about what we should be doing in terms of AI engineering and that's our goals, there is definitely a sense of urgency to solve this issue somehow. And if we believe that full self-driving technology is still a long way, then we have to think what we can do today to improve road safety. Eventually, Continental and myself and my team, we have been working on technologies that are similar to self-driving, but it's not the level of full autonomy. So this is what the market calls advanced driver assistance systems. This is the industry name of this technology. So these are systems that eventually understand the environment around the vehicle and that are able to act in this environment, able to take over control of the car, but it's not a fully autonomous system. It's not able to take over in every situation, so it only realizes partial autonomy. The driver is still kept responsible, but these systems over time are getting more and more accurate, more and more safe and reliable. So So this way, they have a potential to dramatically reduce the risk of road accidents on the road. And at the same time, they are affordable and they are available today, because some of the challenges with full autonomy, legislation and standardization on the roads, this is not a problem anymore for advanced driver assistance systems, which are in cars in new cars, series produced new cars for many years. And they are getting more and more standard in newly shipped cars. And eventually they have a potential to get to customers, not just in the very developed and rich countries, but also low to middle income countries where they have an impact actually on road safety in these areas. So us in Continental, we are definitely very much interested in developing these systems and using state-of-the-art AI technology to power them. So AI is essential, just as in fully autonomous driving, also in ADAS systems, to get a very accurate perception of the surrounding of the car, to understanding that. So Continental has been developing machine learning solutions for these types of systems for many years now. We are busy, and my team is busy with AI development for perception, to understand traffic, understand moving objects, static objects, movements, drivable area, road layout, traffic rules, and so on. It requires a lot of very complex deep learning models, and these are becoming parts of even larger complex software components. So this is what we work on. And today, I want to show and share some of the learnings we had on this journey to develop these solutions. So you will see 6+1 points from me today, where I share with you some very interesting lessons that we have come across on our road, while powering Continental systems with best of breed AI, deep learning, and perception solutions. Of course, I'm not in the position to share the whole story of this development. This is why I just picked a few points for you today. And I also suppose that some of these points you might have already come across if you ever worked with machine learning, with deep learning, with any type of artificial intelligence development. Yet, I believe that some of these points and some aspects of these points might be eye-opening for you. And I'm very much interested in your feedback after this talk, and perhaps your questions, how you think about this. So let's get to it, and let's already jump into the first point of that. So we are developing ADAS systems, AI for ADAS systems, which are safety critical systems. So it's very important that we engineer by the highest levels of engineering principle and process maturity. We have complex AI components, and the development of these definitely needs project-specific software tooling. Also, these automotive projects, they have a faster time to market than full autonomy, as we talked about before, yet they can have very long technology cycles. So a full development cycle of an ADAS system can take up to 3 to 4 years. Of course, software engineering within that spans a shorter amount of time, but it's still, we are talking about lengthy projects and involving really many, many people working on those. When we start a development, we of course have to create our tools for developing the machine learning solutions. And data might not be available in all quantities at the beginning of that. Perhaps we don't even have any data when we start a project from the very specific sensor we are going to work with and have to deploy to. So this is a challenge. Now, of course, specifications can also be a bit vague, like years before an eventual shipment of an algorithm. And if you think about what you would train, what you would select as a deep learning model, as a perception deep learning model, let's say a computer vision model, 2 years before shipping a project, eventually that model might be just, 6 feet under. It might be completely obsolete by the time you have to ship. So you really need to be able to design with time in mind and create a future-proof design for your pipeline. What does that mean? So your design shouldn't really favor specific architectures, specific modeling principles, and definitely very little about technology itself. So how that should be carried out in practice, you can ask yourself, if I create the pipeline I want to do, how easy it is to integrate, let's say, a new paper that I just read about on arXiv or some of the vision conferences. So what can I do about to really make it as flexible as possible for new ideas to come? And you might think that, okay, it's perhaps safe to design the system for convolutional neural networks. I will even ask you whether you wanted to do that. Who knows in 3 years from now whether we will still use convolutions for our deep learning models, just thinking about the recent progress with transformers. So it's a very big challenge, but it's possible to solve, and conscious planning and conscious iterations on the pipeline development and these thoughts early on can be very valuable. Okay, so then I would go ahead with a second point that we have learned during our journey, which is how to combine and how valuable it is to combine creativity of engineers with the discipline of controlled experimentation. So those of us who came from research, we see the value and we really see the power of controlled experimentation, in which we can make progress with our deep learning development and yet measure very specifically how are we getting better than a baseline before. Yet the biggest power we can use from our teams is a team of empowered, smart, creative people with diverse perspective, an inclusive engineering process where everyone can take their ideas into the common knowledge. So how do we marry these two things, so to say? How can we save the best in both? So in large and complex projects like AI development for ADAS systems, we require really many people working at the same time. Many times, actually, people work on the same deep learning models simultaneously. So one might optimize the encoder convolutional network architecture. The other can optimize the representation of a task output layer. And the third one can compile a new data set that focuses better on corner cases. So how do we make sure they don't step on each other's toes and they don't make progress in directions that are not compatible with each other? So we can use our tooling to fix that. Progress is always made in small steps, and we must be able to measure these small steps and measure these small steps of improvement independently from each other. So it's very important that when we do experimentation, we always have the baseline, which is a previously delivered model. Let's say at the very beginning, it's a stupid baseline model, and we iteratively improve over that with each and every addition of the engineering process. So we get very powerful if we embed most of this engineering process into our tooling and into the way we use these tools. So for instance, it's pretty important that we have a well-established abstraction of our data sets. So data sets are moving, data is constantly arriving into the system as time progresses. And of course, we get more and more corner cases covered as we move on with the development process. So it's very important to keep track which of the models eventually train on which data sets, so that they become really repeatable and we don't mix up factors of improvement, let's say something implemented in the model with something else changed in the data. The same way we can think of the model. We want to have an abstraction and we want to have a version control for all the data set. Repeatability, therefore, is very important. And this way we are able to test the impact of changes independently from each other. So by the end of the day, when we merge multiple changes targeting different portions of the deep learning architecture, we have a very good chance that eventually their effect is adding up and they don't cancel each other out, or we don't make steps not in the same direction. This way we can also understand why our performance, why our accuracy is improving over time, and these learnings can be very valuable for the team to be even faster and better with the development. Okay, so let me then talk about the third big learning here. The power of automation and using automation in the development process, and also to close the loop, so to really be able to automate as much as possible. This is actually a very powerful thing to do, and we do have more and more ML ops tools in mature enough stages available in the open source market and also other sources. So we are able to use continuous integration of models, also automation of the trainings, orchestration of the trainings. If we are lucky enough to use a very powerful GPU cluster, let's say, the orchestration of the trainings can be automated. We can think of automating the evaluation of the trained network, the calibration of the network, where we try to map the output confidences of, let's say, a detection with specific precision and recall levels. Who knows? We can think of automating quantization of the networks if we really want to embed into embedded hardware devices, or pruning if we have runtime limits, or even the deployment itself into a larger software component. So how do we do that? It's the best if we walk through the development workflow and we ask questions: where are the manual steps needed to release a specific version of the software, of the deep learning software we are creating? Wherever we come across a step like that is done manually, we must really ask serious questions. Do we really need to keep that manually? Many times the answer is yes, of course, because that's a complex step. But it turns out after iterations and thinking that eventually it is possible for most of the topics that I talked about to have very sensible ways of making that automatic, actually, and encoding some sort of decision logic in the automation that really selects the optimum of the decisions every time. We should optimize for iteration time. So the KPI, how well we are automated, should be, do we have at all any manual steps left in the process? And secondly, what is the iteration time from, let's say, model training into a final deployment? If we optimize on that, it's not a big magic, but eventually these fast iterations make the development workflow extremely powerful and very cheap. And cheap iterations will encourage bold ideas of engineers. They are able to try out more things and more ideas. And failure is fast, and it's also painless, because mostly we use machine hours and not really engineer hours. Why it is important to do early is, first, we might have time in the early phase of the project, as long as we don't have enough data, let's say, or some sort of other input is missing. But also systems are reasonably simpler at the beginning of a project. And more importantly, extensions of the system will have to become automatable. So once you start with a very minimalistic but fully automated chain of deployment, whenever you add a portion of complexity to that chain, you will have a choice whether to break automatability or whether you keep it automated. And of course, we can think that this is a strong encouragement to keep everything automated for that process. Okay, so this was the third one. The fourth important learning that we have come across is related with data. So data I think in many projects, it's probably not very specific to ADAS system development, but it's like really like a bit like vaccines in Europe in the pandemic, right? So we expect them to arrive already in big quantities, but eventually reality is that sometimes they arrive slowly and in smaller quantities. So we have to figure out workarounds how to do that. It's pretty clear that if we engineer safety critical systems, we cannot just use out-of-the-box models. So we really need specific data from the target systems to fine-tune the performance on the corner cases we really need them to work on. But we cannot wait for months and months for the data to eventually make progress with the initial versions of the model. So we have many techniques available in deep learning and in machine learning, some of which are quite popular lately, which can help in this problem. So you can think of utilizing data that is, somehow related to the problem you are trying to solve. but also it's not the very specific label data you really want from your actual target system. So you can use transfer learning, you can use domain adaptation, and you can use now a very wide range of potential solutions for semi-supervised learning, unsupervised learning, contrastive learning techniques that we often label as data efficient learning in our engineering process, in order to really see what is possible, to validate our implementations of the models, even to be able to rank different approaches and compare them to each other while we are waiting for a large enough amount of data from the very specific target systems we want. So this way we can leverage unlabeled data or weakly supervised or noisy labeled data and data from different tasks, perhaps even different domains. Simulation is one way where people tend to think about as a very promising solution, where basically graphical rendering engines are used to create artificial training data with very high fidelity and very realistic optical characteristics. While there are some others who have legit concerns about that technology, whether they really capture all the variability in the world, we do see that in the latest time there has been really tremendous progress in that area, and we have very remarkable solutions for that as well in the scene of simulation. So it is possible to make that. And now for the last few points, I would turn from really a bit of the engineering workflow into more specifically to deep learning. Now, as you know, we have talked about perception models. We want to understand the world from sensorical information, mostly camera images, but also other modalities of recordings like LiDAR, point clouds, or even radar in some cases. So as we have more and more things that we have to understand from our surrounding, we will have to translate them into more and more different machine learning tasks, computer vision tasks. Now, each of them obviously will have its own data set, the labels from which the model is able to learn. And each will definitely have some specific output head. If you think about a convolutional network, then basically the output structure of each and every task must be, of course, specific. But a large portion of that network and a large portion of these deep networks, the encoder, is an open question whether we want to combine that across tasks. So of course, if we have 5 of them, we can, and we have, let's say, a combined inference budget of, let's say, 1 time unit, we can decide whether we want to create 5 separate networks that in average use 1/5 of the inference budget, or we can think of combining them all into one encoder where roughly the encoder takes the full compute capacity, or split it up into smaller chunks that some of the 5 tasks, let's say 2 of them joined or grouped together and the 3 others in a different network. So that way we would have 2 encoders for the 5 tasks. So this is an open question how we do it. And the more different tasks we have in our system, the more compelling it is to come up with some sort of combination, because of course, if we have 10, 30, 50 tasks, then we must amortize the available compute budget to an extent that makes no sense anymore. And the models would be so small that performance would be not sufficient. So it's a very delicate question how we do that. Many tasks are just simply not a great idea to put together in a single encoder. They don't collaborate well. But why do we do it anyway? We do see that in many cases this can be helpful, as others also in the field do see. There is a power that a single encoder can be trained better with better and have better priors for a task by leveraging the other tasks and be able to create convolutional filters for the other objectives as well, and get better overall results in the end. There are, again, as I said, this is a very delicate process. We identified many factors of the training that must be able to optimize independently from each other. And this is also an active area of research, as we understand. So there are still no ready-made answers and out-of-the-box answers how best to do that or how to do that optimally. Okay, the sixth point here is something that is very specific to, again, to our field, when we have actually a very low power, let's say an embedded hardware that has a limited inference time budget. So what we learned, and this is the sixth learning, is that we have to squeeze out the juice of every single flop that we have in our inference budget. So if you ever came across this problem in your engineering, that you had to create something for a low power or reduced compute capacity inference device, let's say an embedded hardware, an edge device, or even a mobile device, and you lost sleep over how to utilize the latest improvements in deep learning, you need to know you're not alone. So this is actually a very very active field of research as well, and it's a very vivid area of engineering to come up with good solutions. In ADAS, we do understand that this is eventually our opportunity. So if we are able to really utilize low-powered devices with good quality understanding of the world and good quality perception, we are able to really ship these models that are available for series-produced cars in very short time frames, as opposed to fully self-driving systems or autonomous systems, which sometimes require like extremely expensive compute units shipped with them. Nevertheless, it doesn't make the problem any easier. So what can we do? Now, deep learning progress is often understood as, we just keep increasing our model size and add more and more data, and this is how we eventually get better and better accuracy in the end. Now, this is not quite true as we do see, and as some OpenAI researchers found recently. So they looked at really the algorithmic efficiency of neural networks, and it turns out that if we look how algorithmic efficiency of neural networks developed over the 7 years after the big victory of AlexNet on the ImageNet challenge, so 2012, what we find is that eventually to reach the same computer vision performance in 2019 that AlexNet provided in 2012 and won the ImageNet challenge, it turns out that we need 44 times less compute power to reach that. So we cannot say it was just that we use larger and larger models and smarter training techniques, but eventually our algorithms got more compute efficient in the end. So it suggests us that there is a large potential also to look into how different deep learning models can be squeezed and adjusted to specific low power target platforms. And there are a myriad of methods there, some automatic, like the neural architecture search and all the variants of that. And there are also manual methods which somehow just create or define the engineering process in a more disciplined way. What we find also is that flops and gigaflops and max and all these measurements of compute power, they don't give the full story. So if we have a chip with a certain capacity, let's say a gigaflop, and we have a CNN, like a ConvNet architecture with a certain compute demand, it might not be that the two would still be real time or run under the same runtime constraint. What comes into the picture and what people tend to look into more deeply recently is also the memory access patterns. So it's quite important that we not just see like the individual computations, matrix operations one after the other, but also how these models reach eventually and hit the memory of these embedded devices, because that seems to be also part of the bottleneck they have. And that takes me to the last learning that we have made on this journey. is that it's very important, and it's basically not possible to make real progress without having tremendous people on board. So it only makes sense to go on this journey together, have no physical or imaginary borders between teams that are working together on this problem, no matter really how many people are involved, and to have an inclusive workforce, have an inclusive process where diverse ideas are encouraged to exchange and be integrated, and to bring in very diverse perspectives. That makes the whole process a lot of fun, and I think I'm fortunate enough to participate with my team in such a process. So with that, I thank you for your attention, and of course now I'm ready to take some questions from you. Thank you.
Thank you very much, David, for the very interesting talk. Listeners, please don't forget to use the poll feature to rate the talk, and it's always very useful to get feedback. And now the questions. So I see two questions to David. The first one is, which techniques do you find most promising when there is low amount of training data available?
Okay. So when you have low amount of training data available, you should look out for similar training data in the public domain. So if there is anything like that, the best you can do is use that type of data. So like public data sources are in the deep learning community, they are quite diverse. So you can find really nice data sets sometimes, which might not completely be what you are looking for in your final application. But there is just a shift of, let's say, the domain of that data set. So that's a very trivial first step. Now, of course, as the tasks get more and more complex and more specific, this is less reliable. So then you might fall back to transfer learning scenarios where you need still some sort of very specific problem-specific data set, but you don't need as much as you would for fully from scratch training. You can think of also using domain adaptation where you have, let's say, a larger amount of data set from a labeled task and a smaller amount with the same task specification, but from different sources. You can also think of few-shot learning for very experimental setups where you really need just a handful of labeled examples. So there is a wide range of that. And lately what came into is also using other regularities in the image data. Let's say if you're working on computer vision and you have video input to your system and some frames of your video is annotated, you might find methods which can leverage the unlabeled frames and somehow use the sequentiality of frames as an information for the learning system. This is what I would say for that.
Thank you. The next question is, why do you think multitask learning is the goal? The alternative is end-to-end, evangelized by Command.ai, making big success. So what's your view, David?
I think there is no single response to that. There is no single truth whether multitask is the way to go or not. It really highly depends on what your eventual tasks are and how your annotations look like. It turns out that there are tasks and annotation types that go together very well. So for instance, if you plan to predict object bounding boxes, but at the same time you're interested in each pixel's classification into a semantic category, and you have training data set for both types of tasks, then you can win quite much by combining those models and get a higher accuracy than if you would just train them side by side. There are other cases where it's understood that certain types of semantics and labeling styles are just not very friendly to each other. They create conflicting objectives and they make basically this multidimensional loss surface a very hard one to navigate for the optimization methods. So it really depends, and currently it takes a lot of experimentation. There are a few, I would say, a few techniques and few heuristics that that come up with a more systematic way to determine whether multitask learning for your specific case is optimal or not. What I see is that oftentimes they don't just strike the right answer, so it takes a lot of experimentation. The more tasks you have, the more you should think about it.
Thank you. An interesting question. Is it possible to outperform a competitor with 1 or 2 orders of magnitudes more data?
One or 2 orders of magnitude more data, I think that can be a very strong weapon in your hand. So I believe if everything is done right, and if the engineering process itself is perfect, that might be the silver bullet. But I think the challenges are not just about data here, for sure.
If there is few data but complex model, then the model tends to overfit. How can you handle this problem?
Yeah, overfitting is a quite common one. So there are many different techniques in the literature, and also I think it's also common knowledge for many practitioners. I think different types of regularizations, dropouts, normalization techniques, augmentation, all can be used to overcome this. I think it always has somehow a limit where you can go. So the variability of your data you can increase with smart techniques, and you can just steer away from your optimization process to find overfit points in the optimization space. But ultimately, it's always the best choice to just have more data if you can.
Are you using simulators to produce data for model training and then deploy those models in the production?
I think the industry is looking more and more into this direction. There are concerns about it, and I think it also heavily depends on which part of the engineering process you want to use that data. But there are parts where this makes a lot of sense, actually.
And one more question, how do you pick which data samples send to label? Sorry.
Yeah, I think this is also an interesting question. So if you have very large data sets, then actually not all of your data points are, let's say, important to the same extent. So there are data points that are more important. So you have different techniques for that. Actually, when it comes about corner cases, you can always think about how confidently your model predicts something. You can even use uncertainty estimations while you're training the model about really the uncertainty in the predictions themselves. So there are these different techniques. They can make sense to be used.
Yeah, another question. How will autonomous AI systems adapt to local driving habits? You could argue that people drive differently in Thailand than in Germany.
That's perfectly true. It's a bit out of the scope of understanding the environment. So I might not be the best person to give an answer on that, but I believe if you apply some sort of machine learning on the behavior of the car, then you can leave some space in your model for adaptation of first the driver preferences, and perhaps in other approaches also to the local preferences. I'm not very deep into this topic, so I wouldn't be able to tell you very specific techniques to do that. But I think in general, this might be possible.
How do you determine the hyperparameters of your deep models? Do you use optimization techniques such as simulated annealing or genetic algorithms?
Yeah, there are different types of search techniques here. Also, there are pretty sophisticated tools to do that. it's a question whether you do like a more grid search-based approach where you try all different combinations, how you randomize your search there, but also there are probabilistic models that that promise to have a faster convergence to the optimal set of hyperparameters. So I definitely recommend to look into some of these techniques. We do use those in our models as well for certain types of hyperparameters, and we do see that it makes sense to automate this and have tools to do that in the process.
Do you need to create different models for different light conditions?
It's always an engineering choice. You might as well do that. It depends on many factors. It would be hard to give a single answer on that. It depends how big of a network you can afford to run in your application, in your use case scenario. But sometimes it could very well make sense, yeah.